Mm-hmm. Okay, that's fine. Are you there? Yes. All right. Okay, ready to start. Good morning, everybody. So we are now going and moving out from the theory part to more practical things. So we will focus on crystals. The first lecture is about that, and the second lecture will be that we will have a walk through how we do the work with the computer. And then you will have this handout to yourself, and we organize so that if you like, you can get, if you don't have these programs, you can get them from us. So you can then do it at home with your own computer. And it's a Windows-based, it has two versions, Windows and Mac. The Windows version is easy to install, it's easy to do. But the first thing we will discuss about the crystals, because remember, when we started the whole thing, that the most important thing is the crystal. So if we don't get the crystal, we don't get anything. And now the idea will briefly go through what is a crystal and how to grow them. There are many methods, and this is really an important thing to do this, that if some method doesn't work, then you can use another. And there are some tricks and treats and things like this for doing this. So that is experimental work. So until now, we have been dealing with theory in a very, let's say, surface level, trying to explain the diffraction and all these kind of Rorty's X-rays and so on and so on. But now we go really to more of a practical thing. So we need the crystal. So what is a crystal? In general terms, crystal is our target. Remember, this is single crystal X-ray diffraction or crystallography. And we can't really do anything if it's non-crystalline. And we can have a powder or a single crystal, but the information we get from these two things are different. With the powder, you can see if it's crystalline material, and you can get some information like unit cell from the powder pattern. But for the molecular structure or atomic resolution, you need a single crystal. And that's now our target. So surprisingly, this first sentence is true. So crystallization is the often most difficult and time-demanding step in there. And you will soon see this. When we get through this, when I will show you how much does it take time to get an X-ray structure done, you will be surprised. Because most of the time, it might be so that 99% of the time you stay in the lab making the compound and crystallizing it, or a complex, or whatever entity you might have. And that's the point. And why it's so? I've emphasized it many times, because when the diffraction happens from the atoms, clouds, or electrons of the atoms in the structure, how they are organized. So the point in there is, what is crystallization? Crystallization is that you let nature organize your objects, your molecules, in perfect 3D orientation. And if this happens, then the diffraction happens. But if it doesn't, then there is no diffraction, there is no information. And that's the idea. So the quality of the crystal determines the quality of the data, which determines the quality of your structure. And if the data is bad, the structure is bad, or even in this case, that you can't even get the structure. And it can be very annoying. So though the idea is that the optimum size nowadays is around 0.1 millimeter. So it's so small that you cannot see it. So you have to use microscope. And here you have seen these images that they are different crystals from microscopic images of different crystals. And the point in there is that we aim the best for our purposes would be sphere. But it's very difficult to grow good spherical single crystals. This is very unique And normally that's not the case. But then the next one would be cube, because it's in the same direction, always the same shape. Why is this? It is that because we hit X-rays with it, then if it's like a thin, like my finger, say the absorption in this direction is much less than in this direction. So the idea is that if it's a sphere or cube, then the absorption in all these directions is the same. So that's the idea. So we aim to have it. And we are in difficulties if it's a very thin plate. So let's say like my hand or even more, then one dimension is very thin. Because what it means, what we need the volume. We need a certain amount of atoms or molecules in that crystal in order the diffraction to happen. And if we have a very thin crystal, then that direction there is not that much information coming because there are not that much atoms in that sense. But that's the idea. And now, this is a very important. Quite often, not always, good crystals look nice. The looking nice means regular faces and edges. Like here, if you look for these things now, they look really like rhomboid kind of things. And this is normally a visual information that this crystal might be good. But just the looks doesn't tell. It's the same as with the persons. Person might be nice looking, but not a nice person. It's the same thing with crystals. And now we can go to, so this actually is a little bit old. We can go to 10 micron relatively easily. 10 micron is 0.01 millimeter. And they are extremely small. And this is for the current instrumentation. The instruments are so powerful that we can study very small crystals. If you have a too large crystal, so let's say that you have a crystal like this, and this would be 1 millimeter. So you would not be able to use this 1 millimeter crystal, but you can cut crystals. So like you cut bread or anything, you can cut crystals also. And then to get the correct size for this. But the point is that if they grow naturally on this size, then we are happy, then we can just do this and pick the crystals. And the idea is that, of course, the more heavier elements they are, the more there is electrons, and if it's well ordered, the more it diffracts. What it means that we can, with the heavier elements like polyoxometalates or something that have molybdenum or tungsten, then a very tiny crystal will be enough. Now, general considerations. Factors which are happening during crystal growth. So the point is that it doesn't appear from air. We have to grow the crystal. Typically, we have to tell our molecule to crystallize. And the process is called the crystal growth. And that is what has a big impact. So how this happens, nobody actually really knows. It's really difficult to tell how the molecules are coming and what is the actual idea of how they start growing. This is completely, I would say, completely unknown. So it's really a mystery still why it happens. There is more and more information coming and also knowledge, and maybe we will have more information because it would be really crucial information to know what there is happening during that time. So one of the things when we are normally working with molecular systems that you have to solubilize them in some solvent. So solubility of the compound is important. So of course you can't grow crystal from a material which is not soluble. If it's not crystalline or single crystal by itself, then you probably discussed about the moths yesterday with Rahul Banerjee talk. If you dissolve it in water, it decomposes. So you cannot. Sometimes you have a system that you cannot dissolve it. But then it means that it has to be single crystalline by itself. Then it's fine. So when we get our target, it doesn't matter how we get it. And sometimes it is a really complicated thing. So the idea is that we can consider in our vessel, you will soon see this kind of a thing, it could be a tube or a flask or whatever. We call it, or we name some of the points where the crystal starts to grow, we call them nucleation sites. So somehow a group of molecules will go into one place and they organize. It's in a very tiny tens of molecules or so, and then it starts to grow from there. And then that is, we call it the synucleation site. And then that's the idea, and then mechanical shaking. So this is easy to understand also, because their process is very subtle. It should be, we should let it happen in peace. But if you shake the thing, it doesn't happen. The shaking is bad. It destroys the process, because it's like shaking all the time, these things. If you get something upon shaking, they will be very tiny. But the idea, they might be too small for us. So that's the idea. And the time, this is of essence. So the point is really that you never can, in advance, never tell how long does it take. It can take from some seconds to months. And you can never know that in advance. So that is a really complicated thing for us, that, for example, a PhD student has a project to crystallize something. And then you wait 9 months and nothing comes out. So it's a really complicated. I can tell you a short story about this length of crystallization. I had a postdoc researcher from Italy, and he was doing this thing. So he prepared, that was their uranium uranyl complexes, a very heavy metal, and then organic ligand in their metal complex. And he wanted to have the structure of these things. So he prepared 90 samples, 90 different experiments in his first 2 weeks. Then he was staying 3 months and waited 3 months, nothing, absolutely nothing. So he went away. I said, oh, this is maybe this is gone, all the work is like in vain. But then we decided, okay, that leave it in the hood, leave it there standing, and we left it there. And then the same hood was taken into use by a master student 6 months later. And the student came to me and says, somebody has left a lot of tubes there hanging in the hood. That what shall I do? Shall I put it in a pin? And then I first said yes, okay, but then I said no. I remember that this was left by this Italian guy in there. I said, don't throw them away. I will check them. And it turned out to be, we got 30 X-ray structures out of this. And it took 9 months. And nobody knew what was happening. And that is really the difficulty with this. It's like both plus and minus, that you can just leave them there and then go occasionally and look, or then it happens by itself or it doesn't. So that's really, and then if we are lucky, we can get really this kind of a crystals. That could also quite, but this looks really strange. And sometimes, because it's difficult for you to see, but here there is this like a star thing, that the tip of the star might be okay. So sometimes it's really bad looking, but it can be crystalline. It can be single crystal. So what we have to do, of course, this is a clear all done in organic chemistry or some other things also, that if you have an impure material, the melting point of that will go down. And this means that it's impure, it's messing up. When you have crystal lattice, it's always at a higher melting point. So we have to have a pure compound, as pure compound as possible, because impure are either they don't crystallize at all, or they create a precipitate, a very tiny crystal, maybe powder, which we can do a powder diffraction, but not a single crystal. They're too small. So the idea, normally this means smaller crystals, and you might have sometimes, if you're lucky, this means nice, that your impurity crystallizes with your compound. And then you get the structure of your compound and the impurity at the same time. But this is very rare. Typically, they don't like each other, and that's the case. So the point is, when we purify, the purification, of course, minimizes all the other possible things what we might have in there. So we always aim as pure compound as possible. And the one, which is interesting, by doing successive crystallizations like we do in organic chemistry, we'll purify the compound. So we dissolve it, crystallize fast, we get the crystalline material, we separate, we dissolve it again, do the same, then repeating. In this way, typically the impurity stays in solution and we get a pure product. This is one of the easiest way to purify materials. And that's the idea. You can do the conventional or other purification methods. So that's the idea. But the point is, what is very important, we have to know, or it's very helpful to develop a solubility profile. So the solubility profile is a very simple thing. It's just information where does your compound, or in which solvent your compound is soluble, completely soluble, and where it's not soluble at all, and then where it's intermediately soluble. So these three informations are crucial because we can then modulate this thing, because the idea of what we want to do is that our molecule will not be happy in the solution and it wants to crystallize. So we've tried to persuade it, and this is the way for us. We change the environment, and that's the idea. And then, of course, clean glassware is the point, because if it's not clean, that will bring impurities, and then, of course, we are in problems with this. And the idea is that when we are doing this, now depending on the amount of material you have to work with, I would say that in practice 10 milligrams is like a minimum amount which is reasonable to work with. The more you have, the better it is, because you can do simultaneous experiments. You can do one experiment and second, the third, like I told you about the Italian guy who made 90 experiments because there was enough material to do this. So that helps us to, because we can't be sure which of them works, so let's make many. So that's the idea. Because what we can do, we can change the conditions, and the conditions can be solvent. Select 20 solvents. Then you have a 20 experiments. Then we can use temperature, select different temperatures. We can have that in a low temperature or room temperature or an elevated temperature. That's fine. Or we can use different concentrations. We can have a low concentration or high concentration. And then we have several techniques which I will teach you. So now, if you look this carefully, you can easily see it's very easy to make 100 different experiments and let them go simultaneously. But normally we don't do this. Normally we'll try to think in advance, develop their solubility profile, and then say, okay, my molecule has this and this kind of functional groups, or this is a metal complex and we can't dissolve it in water, so maybe it's a different solid. So thinking in advance what we have will make our life much more easier. So we aim already, like by thinking, figuring out what could be the best ways of getting the crystal. And then the solvent is the thing. We, as we spoke, 99% of our cases is so that we solubilize our target to somewhere and then do something for that solvent where the target is, that it wants to come out as a single crystal. And the point is, if our target molecule is too soluble, nothing happens. It will make a class. So all the solvent evaporates and then nothing is there. And the idea is that either there is nothing or it's very tiny crystals. And then the point, avoid the solvents which make a supersaturated solution. So this is an idea that you get so high concentration at a certain temperature, and when you tap it, it will solidify. So their concentration is too high. This is rather rare, luckily rather rare situation, but can happen. Because by shaking, it will like a freeze the whole thing. But that's the idea. Supersaturation also gives too small crystals. So nucleation, this is a really abstract thing. That's the idea that we spoke about nucleation sites. But nucleation is the phenomena where a few of these molecules meet, and then they will attract the other molecules. And that's the idea. And then we have fewer sites. So the idea, and then there will be a grow on that. It starts to grow on that part, so it can grow bigger. So if you have a lot of these nucleation sites, then we have a lot of small crystals. But this we don't know. We don't see, we can't tell that that's a nucleation site and that's not. It's just by chance what happens in there. And the idea is that in crystallization, sometimes if there is, for example, dust in the air, and this dust goes penetrates to the solution in the technique what we are using, that might act as a nucleation site. So it might grow a nice thing. The dust is so small it doesn't interfere anything, but the crystals grows on it, because then maybe there is a one dust particle and then 10 to the power of 8 molecules. So then one dust particle doesn't mean anything. That's the idea. And then the mechanics, this is the shaking. This is the idea that if you do shake your material or the vessel, what you're doing, mechanical disturbance will also do the same thing. Any disturbance is the idea that if it's shaking a bit, if you put it on top of a fridge, the fridge is shaking, that's bad. Normally it doesn't work well. So let the crystals grow with the minimum of disturbance. They are, I can tell you in real life, they are so sensitive that even looking at them is not okay. So what it means, that of course not joke, that you'll just leave them. So you do it, you put it in a nice place, and then you go away. And then in the next day, you come and look without touching this thing. They look, okay, can I see anything in there? If not, go away and come back in the next day. So this kind of a thing. And sometimes it helps if you forget it. For some reason, it's quite interesting, the idea that you just leave it there and then I left them 2 weeks ago. Let's go and see what it is. Here's a crystal. So that makes it's really a complicated thing to plan in advance. Okay, now the crystal will come on Monday at 8 o'clock in the morning. No, that doesn't work. But mechanical steering is always bad. So always avoid this. And then time. I already told you about the story about the time. It's something also you don't know. But now when we go to the techniques of different techniques, we can modulate the time. So we have possibilities of somehow have a control for the time what is happening. And then it is of essence. So time required to obtain good quality crystals can be anything from minutes to years. And this is really true. This is not just a sentence. The idea, but if you want to have these, be patient. So if you are rushing, I already got something, and then you go and put it, no, it was not good one, and then you destroy the crystals. So be patient and see, and then remember they are very small. So we have to always look them by microscope. So that's also the idea. The point in there, by a rule of thumb, that if you have a test tube and then you can see crystals, they are already too big. But luckily you can cut them smaller if you are clever with this. So now we go to the techniques. So how to do this in real life. These were the general things that you have to take into consideration. That's the normal work in the lab, what you do. Whatever kind of a target you have, would it be purely organic, either could it be purely inorganic? There is a method also. It could be like yesterday you heard about the moths and the coughs. It's the same thing. And actually yesterday Rahul Vanaria was showing one technique. This technique was used to prepare the material, but it's also a technique to crystallize, make crystals. You will see that later on. So that is the essence. It doesn't matter what you are studying, what you're doing, what is your target, but the principal idea is to be able to control what happens. And this control happens with different techniques. So the simplest, of course, what you can consider is that you take sugar and you dissolve it in water and let it stand. The water starts to evaporate, and in a certain time there will be a concentration cut or concentration limit where the sugar crystals or sugar molecules are seeing the other sugar molecules and they start forming a crystal. And then the crystals form in there. And that's the idea. It's a slow evaporation, it's the simplest. And now it's easy to understand the idea. Of course, the polarity makes a big difference. You use a non-polar solvent or polar solvent, is it aprotic solvent and so on. You also have to think about this when you're looking your target molecule. So if your target molecule gets considered a metal complex, for example, then you have to be sure that you will not destroy your metal complex when you are dissolving it. So that's the idea. But that's quite, I think, intuitive when you're actually working with this kind of, because if you prepare, you know already something how your target behaves. But that's the idea. Slow evaporation, make a decent, again in here is if the concentration is too low, nothing happens. But if the concentration is too high, it comes too fast. So again in here, information or knowledge, let's say that how many milligrams of the compound dissolves in that given solvent in room temperature, for example. That is a very useful information. And then when you know this, then you make a lower concentration, maybe 1/2 of it, and then let it stand, test tube or anything other, and then let it evaporate, and then look what is happening. But of course, it's easy to understand that when you have evaporation, if you don't look into it, if you forget it somewhere, it will get dry. And this is bad, because often crystals contain solvent, and if it gets dry, it cracks it destroys the crystal. So you have to, in a sense, follow the slow evaporation is a technique. You have to follow how the evaporation happens. And typically it's then, I don't have a blackboard here, but I could draw. So the actual idea is that you fill up the test tube with your solvent, and where the cartage molecule, you made a mark on the upper level of the solvent, and then you just follow. Okay, now it went 3 millimeters down. Now it's 5 millimeters, it's 1/2 centimeter. And then you observe what is happening. This is the way to do this. And then can be saturated or nearly, it doesn't matter. So it depends on how, what is the behavior of your target molecule in there. And then you can slow it down very simply. So if it's an open tube, it goes faster. If you take a test tube and put ether in there, it goes quite fast. But what you can easily do, you just cover it with something. You can put a glass plate in there, or you can put a rubber septum in there, or anything. You can put aluminum foil and make small holes in there. All the other things, everything is allowed just to control the evaporation rate. And normally, the slower is the evaporation, the better is the result. Because then it's a slow process. It has time to find the best conditions for the crystal growth. And that's the idea. And now, again in here, when you do you do the slow evaporation, place the container in a quiet, out-of-the-way place. And let it be. But now, because it's evaporating all the time, the concentration will go higher and higher when the solvent evaporates. There will be a case when the crystallization happens, if it happens at all. But if it happens, then what you should do, oh, now it's done, you should close the vessel and keep it, because then they are safe. Don't let it dry, because you don't know if the crystals contain solvent, and if they contain solvent, if they dry, they die. So that's also a practical thing to do. So the idea is that keep it. Now, this is now the crystals obtained by slow evaporation. They are there. Sometimes you have stable crystals which are stable in the air. Sometimes, especially large supramolecular or whatever structures are there's a lot of solvent. And then it will destroy immediately when you take the crystal out of the solvent. But this is the idea that if this happens, then you know, okay, my crystals are very sensitive. I will keep them in solution. There is techniques why how we pick up a crystal from solution and put it in the diffractometer. So now the key success is to control the rate of the evaporation. So that's it. If it's too fast, that's your. And then don't let it go to dryness. This is actually what I indicated. And the point is that in some cases, it happened, and happened many times to me too, that okay, by accident it went dry, but then the crystals had formed in the wall of the tube, and when you try to take them out, they're glued in there. When you try to take them out, they crack. So it was really frustrating. Oh, very nice looking crystals, probably very good single crystals. When you take them out, when they dry, they die. So they crack. And that's the idea. And believe it or not, anima tube is a very nice vessel to evaporate. It's a very thin, long tube. And when you have about 2 centimeters or 1.5 centimeters of solvent, your compound in there, if you are doing animal research or animal research tell you, okay, it's a pure compound, then you just let it evaporate in the animal tube. And then look for that in the animal tube. Okay, now the crystal is there, very fine. Then you can even crack the animal tube and take the crystal out. So this is a very simple way, because you have done the work already, then why not let it evaporate from the animal tube? That's the idea. Then the next easy way, which is more safer in certain sense, is slow cooling. So the idea is that the evaporation you have to control, you have to somehow survey that it doesn't go to dryness. But now slow cooling is a reverse technique, in a sense that now you don't evaporate the solvent, you lower the temperature of the solvent. And this is done always with a closed vessel. And then the idea, then there is no evaporation. You just close a vessel and put it there. But what you do is that you heat it out. So you look for a system that your molecule is soluble in elevated temperature, but not in low temperature or lower temperature. Let's say that it's completely soluble in 70 degrees, but it's not soluble in room temperature. So what you simply do, you put your substance in the solvent, you heat it up to 70, then you close it, put a cork on, and let it stand. And now, upon standing in the air, depending on how large is the volume, it will cool down to the room temperature, and then the temperature gradient induces the solvent crystal growth. And that is a very nice technique in that sense that if this works, then the crystals are safely in solution already. Then you have to just pick it up from the solution. And that's the idea. So the point in there is that you can also do it in a different way, that you start from the room temperature and you put it in the deep freeze. So you go from 25 to -20, and then the crystals grow when you go, let's say, to -10. But now there is a difficulty with this, because if you now take that tube where you crystallize the vessel to the room temperature, it will dissolve back. So what you have to do, you have to be able to separate the crystals which are formed at the low temperature at low temperature, to remove the solvent. And one thing is, of course, that if the crystals are on the bottom of this thing, you just quickly remove the cold solvent and then keep the crystals in there. They might survive when they are dry, because they are soluble in the solvent, not in the air. But there are also techniques how you can actually do this in -10 or -20 or so on. But this is a rather special technique, but it's possible. So it doesn't matter what is the temperature range, but you have to be able to then handle the formed crystals so that they don't dissolve back or they don't crack. So now we are going to the technique what was shown by Rahul Paneria yesterday. He didn't talk about this, but this is actually, this is not the freeze-thaw system, because this is only making a vacuum inside a tube and then heat it up. Because you can do it reversed. And this is actually what happens. And this is called a hydrothermal or solvothermal method. And this hydrothermal means water, and the solvothermal means any other solvent. And it's a very simple technique, but this needs instrument. The first two ones need only a glass tube, for example. It doesn't need any instrumentation, but this needs. So the point in there is that this is typically done for MOFs and other materials which are not then soluble anymore when they are formed. So we have to form them, the complex in situ, and crystallize in situ, and then get it out from there. And this is the thing. So the sample is placed here in this kind of, this is a Teflon tube, and it's insoluble. All the components what you put, like discussed yesterday, they are all insoluble. You just mix them up. So let's say that you have a component A and component B, and then you have your solvent, and they are not soluble. Then you place it in there, you close the cork, you put it inside the steel what we call a bomb. Then you close it, and then you place this in an autoclave. So you put it in an oven. This can be done in an oven also. It doesn't need to be like this, but you need this kind of a safely secured system which tolerates high pressures. So what happens in here is that now when you go and heat this mixture in a closed vessel, clearly up, much higher than the boiling point, it creates a big pressure. So now at the same time you have there in the solvent, you have a high temperature and high pressure. That will force the components to dissolve. And then when you cool it down, what you do is you keep in there, you keep it like he was keeping 7 days. You can keep it 1 day or 2 days or so on. But the point is you keep it long enough that all the components are solubilized. And then what you start to do, you start to very slowly cool it down. You let it cool down slowly, and the slower is the temperature decrease, the better chance you have having good crystals. And majority of MOFs are done in this way. They can be done otherwise, but this is a very neat way to do it. Or some other complexes can be done. Typically metal complexes done like this. But you can also do a chemical reaction. So you take component A and take component B, which are not reacting under normal conditions under that solvent. But if you put it in autoclave, you in a sense force a chemical reaction between A and B happen, and then you cool it down. You will then be able to quite probably crystallize a product C, which is coming out from there. So this is a very nice technique, both growing crystals, but also making reactions. And it's called hydrothermal when it's water, and solvothermal when you have anything else. But it needs gear, it needs the instruments for this. You can't do this in our, because it has to tolerate high pressures. And you can see here that it's really a heavy metal or thick metal container. But it can be done in a normal oven. If you have this bomb, you just heat the oven to like what I was saying yesterday, 120, keep it there for 7 days, and then let it cool down. And then if you are lucky, then the crystals have merged here. And these crystals are then ready already. You don't have to do anything. You just pick it up and put it in the diffractometer. You don't dissolve, do anything, because they are formed in situ in the reaction. But now there are other techniques which are more practical. They don't require any special tools. And there's much more control in here. And these are diffusion methods. So before we spoke about, we always spoke about solvent. We spoke about solvent in a singular form. So using a solvent, the methanol or water or so on, and the other techniques also, either solvent evaporation or cooling down or solvent thermal reactions. But now we take 2 solvents. And the idea is that if we have this is particularly good for very small amounts of compounds, because what we are doing, this is a nice cartoon of it. We are now discussing the solvent layering technique for this. So we take a long tube, this is a nice thing, and we have 2 solvents. And now the point in there is that our molecule is dissolved in the solvent S1 now, in which is completely soluble, but the solvent S1 has to be a higher density than the solvent S2, what we put on top of it. And now there is a layer. So there is actually, this is the bottom layer and upper layer, and then we have here the interface between these 2 layers. And now what happens, this is a very sensitive technique, and it doesn't tolerate at all movement. It's very easy for you to understand, because what we want to do here, at this stem remains calm, but what happens here, this S2 starts to diffuse into this S1. So it means that the local concentration in here, or that local solubility of our target in this area will go down, because it's not soluble. Our target is not soluble in S1, but it's soluble in not S2, it's only soluble in S1. So now we change the local concentration of our solvent in there, so it wants to crystallize. It doesn't want to be in here in this area and any other than crystalline form. And this is a very nice technique, but it's rather slow. This might take weeks or so, depending on how weakly or how quickly the S2 diffuses into S1. And this is a very nice technique. I know that Makoto Fujita has used that a lot in crystallizing MOFs, for example. And that is really nice. And then the idea here is one example, dichloromethane, diethyl ether combination. So they are heavier and lighter, and then shoot the difference. And then, of course, you have to close the vessel, because if you don't close it, it will evaporate. But that is a very nice and neat technique. But this requires a really skillful person, because you have to be very carefully layering the solvent, this S2, on top of that. You should not mix it here at all, because it will precipitate the compound. But that's a very nice technique, especially if you are not in a hurry and you can leave it for 1 month or 2 months in a nice place where there is no shaking. This is another version of the same thing. The idea is that is the idea that you place your molecule in a solvent, like solvent number 1 here, and then you close it with the cork with a small hole. And then you merge the whole thing into another solvent in a closed vessel. And that's what happens through this small hole. There two will diffuse there. And then the local concentration in here will change. So this is a little bit easier technique. And it's called, this is the solvent diffusion. And that's the idea in there. That's the very simple thing to do. And this is much more easier in practice than the long tube. But the long tube often offers better nucleus and sites in there. It's like an enema tube. When you evaporate an enema tube, it's a very nice. Nobody can really tell why is this. Maybe that it's the movement of the solvents, and so local concentrations are more concentrated in the small tube. But that works fine also. It's a very simple technique. And now convection. So this is a tool. You need this kind of instrument. And the idea is this is available. It's a class, this kind of a reversed A. And the point in there is that this is also a cooling method. That what you do, you actually have your sample here, and it's not soluble here in the native temperature. So it's now insoluble in here. But what you do, you heat it up here and there. So that part of the thing is warm. So it starts to rotate there. So there will be a current flowing, or convection flowing on this direction. So it will take here this part, solubilize your compound. It goes in here and it comes in this part. And now there's a cooling. So we cool this part of the solution. And this cooling, it's like slow cooling. Then it induces precipitation or crystal growth, if we are nice. And then the crystals drop in here. And then when everything goes fine, because they travel.
Hello, hello.
Yeah. Okay, it works. So we will do it now, like this. So that's the it's a tool what you can have. You can use this kind of a tool for this. And then when you have done it enough, when the crystals emerge here, then you can then separate them, pick them up from here and put it in the diffractometer. I've never personally, or my group have never used this. But it's in some cases it's quite convenient and easy again. And the point in principle, it's closed again, that there is no evaporation. It's just cooling. It's kind of a controlled cooling. And this is a rather nice thing. But then the method, what we use, let's say 90% of all the time, is vapor diffusion. And this is a very practical technique to do this. So it's a little bit more demanding, of course, than the slow cooling or slow evaporation, but it's nearly as simple as it is. And it's very easy to do. So it works like this. So the point is that you have again a solvent S1 where your compound is completely soluble. Remember, that's why the solubility profiles are very important. And then you place it in a tube like this. It can be open or it can be like this, that there's a cap and some holes in here. It can be open. And then you have another solvent here, S2. But now the vapor pressure of this S1 should be lower than that S2. So the S2 will create here, this is a closed one, it will create a gas phase. And now this gas will then go in here and slowly diffuse in here. And now this level will go up because all the time there is S2 going into S1 and then the concentration. So the solubility of our target molecule will be smaller and smaller all the time. And this is a very neat technique because it's closed. You can see, and this is a real life. So this is about 3 centimeters, 4 centimeters. So you can see there is a cap closed bottle. Inside that, there is a smaller one. There is no holes, that's open. There is a yellow S1 solution surrounded by S2. And now, in this area here, the crystals are growing. This is a very good technique in many ways. Because the point, everything is closed. There is no evaporation. If you use open or these kind of, not open, but clear vessels, you can see what happens by your eye. So, okay, yes, that's that. And once you see something happening, or even sometimes you might create colorless crystals, which you can't see by your eye. So it's very simple. You open the cork, you close this cork, and then you go to the microscope and look, okay, there is some crystals already now there, and then you keep the cork closed, and then you pick up the crystals from there. Or if it's not, you can open the cork and put it back. And this can bring you crystals, I would say, within 1 day to weeks or something like this. But it's really nice and safe. You can just leave them. You can make many of them, and you can just leave. Look, each of them. Okay, this looks that there would be crystals in there. I will check. But this is a very, very good technique to do this. Then there's more techniques which are useful, very good ones, also in many respects. Also, you can do reactions with this. So if you want to create an inorganic complex, a metal complex, or this kind of a normal coordination complex with a metal and ligand, this is a very neat technique to do this. So it's called the reactant diffusion. But for that, you need so-called U-tube. We know what the U-tube is, but this is a different U-tube. So the idea is that we place here at the top or the bottom of the U-tube a gel. It could be silica gel or in principle any gel which tolerates these two solvents. So of course the gel has to be something that it will not be dissolved by this solvent. So what we do in the red solvent, we can have our molecule, or we can have a component like here reactant A. And then on the other side, we can have the other solvent which is our compound is not soluble, or we can have a reactant B. And then we just let them be. I'll close this normally. Of course, we don't want to have evaporation. And now what happens? That this red reactant A starts to diffuse in this direction, and this reactant B starts, and here in this region where they meet, the crystallization happens. And this is a really, it can also call that a gel crystallization. So it can be, it's a very good, I know one of my colleagues has done a lot of pharmaceutical morphological studies using gel crystallization. By modulating the solvents and the gel itself, you can induce something happening. Because consider that you have a chiral gel. Then you have a chiral environment. This is a really nice way of modulating the system during these changes and seeing what you can get out. And that is a very nice thing. And then it gets used to, especially for metal complexes, this is a very convenient way to do this. And now, if you are working on a charge systems, so you have a metal complex, for example, or organic cation, which has a positive charge, we have an additional variable in addition to everything what I've shown. That is the anion. And now it has a big impact. So the anion can be the key on what it crystallizes, what doesn't crystallize. So that is also the idea that you have to think very carefully which kind of anion you are using if you want to have a crystallizing single crystal from a charge system, so salts. And the same applies to reversed. If your system is anionic, like these MOMs are, metal organic frameworks, of course, can be, but also these Soft-Oxometalates are typically anionic. Then it plays a crucial role which kind of a cation you're using. And that can change everything. But that leads us more possibilities. So you can have 10 different anions. Everything else remains the same, but you just have it chloride, bromide, iodide, triflate, sulfonate, whatever kind of a thing, even very large ones. And that might help. Again, nobody knows in advance. So you have to make a testing. You have to test what happens and so on. Sometimes you're lucky, the first thing works and so on. Or if you have a cationic system, so that is the different kind of a thing. PF6 is a very nice non-coordinative anion, because if you have a metal complex, sometimes you don't want to have the anion to be coordinated with your metal complex. So you need And then if you have an anionic system, you want to crystallize it when you use alkali or any metal cation. It will coordinate to your anion in the solid state. That's a bad thing. So then you use non-coordinating cations like EMA. So you can, there is a really big modulation possibilities when you are working with non-molecular systems, so charge systems. So with the ionic, it's like molecule because it has a positive and negative charge in there itself, but that also can help sometimes that the charges will interact and then it will create a nice crystal lattice. Now, there are ways to do also other things. So you can start to play the hard game, and the hard game, yes, please. No, that's fine. Okay, thank you. Now it's better. That we can play risk. The other methods, what we have been discussing now, always rely on a pure system. So pure means that we have one target and we do everything to get this one target on crystallizating, making the crystal. But it might be that everything what we have done doesn't work. We have done 50 experiments and always fails. Either we don't get any crystals or we get powder or whatever. So then we might try, depending on the system, we might try of adding something. So making it deliberately impure. And then we are talking about co-crystallant. So we add a component B. So we don't want to, let's say that we have a component A, it doesn't crystallize, whatever we do. But then we think about it, okay, maybe if we add a component, a molecule B in there and crystallize them together, if they make one-to-one complex, and this complex then crystallizes. That is a chance, but there is a big risk because you, at the same time, you make it impure. So now the B might even disturb it more than it was by itself. But that is something like this. So the idea is that we call it crystallization aid. And this is, it's also, I have many cases like this. So that we had component A, we tried everything, 50 different tries, no way, no crystal. Then it's okay, let's try to do this co-crystallizing things and add another component. And we thought about, okay, maybe there is, let's say, hydrogen bonding or pi-pi interaction or any kind of additional interaction between these components. We did it, and it turned out to be, yes, okay, we were lucky, we got 1-to-1, so there was both A and B in the crystal structure, which was there. So at the same time, we got the structure of our target molecule and then the component B. But it can also happen so that the B induces crystallization. So the actual idea is that you put it in there, but it doesn't come. It makes the crystal, but it doesn't come with the component. And this is really amazing. So it's the B acts like a catalyst for the crystallization. And we have had a few of these kind of cases that's the case. Also, it can be sometimes with the solvent, that you dissolve your compound in a solvent, you crystallize, whatever method. It might be that the solvent comes with your compound because it makes a better crystal lattice with the solvent than without this. Or it might be so that it is there, but it doesn't crystallize. The molecule by itself crystallizes. We never know this in advance. It should not be a big surprise that, okay, there was a solvent molecule. But it can be also another component. And of course, if you have a cationic species, then that's the anion is the B component. Changing the B might change everything. Or if it's the other way around, then you change the cation, because you cannot separate them. But in the molecular world also, if you have a neutral molecules, it can be done. But it's a high risk that you will not get anything. But that's the idea. And then, if you are working in water, you can change the pH. And this is a typical trick for you have a very complex amine, for example. And then you try to crystallize, it's always an oil. You don't get it, always comes as an oil. So the easy thing in there is add, let's say, hydrochloric acid or hydrobromic acid to make a salt out of it. So you protonate the amine to make an ammonium cation, and then you have a salt. And salts, by default, always crystallize better, 99% of the cases, than a non-charged system, because you have the electrostatics there. So that's a trick. So you still have the compound, but now it's just a protonated form of your compound. That's okay. It doesn't matter. That's the idea. So controlling pH can modulate the thing. You can do it with the co-crystallant, or you can do it individually. So as you can see, we have a huge palette of possible means of growing the crystals. And the difficulty that we never know that in advance. So that is the idea that if I get a sample from somebody, I can only say, okay, I will do my best, but I can't promise anything. The only thing I have to do everything from the beginning to the end in order to see how it worked. We are always lucky and when we see the single crystal coming out. Okay, now we got the most difficult task is done, then go to the diffractometer and do the measurement. That's the idea. We can also do this seeding, crystal seeding. So that sometimes helps that you add a tiny crystals in the saturated solution of your thing, that seeding can help, that it induces. So it's like a kick for the process. We have never used this because our systems are too complex, but this is being used in some pharmaceutical and industrial crystallizations. That you're seeding sugar crystals normally when you crystallize sugar. Normally they use this seeding for this. And then a couple of very unique systems is sublimation. So you can actually do, it doesn't normally work to anything else than purely organic compounds, is the idea is that you need a tool again. So your compound is here, you draw a vacuum, that the whole system is in vacuum, then you start heating it up. So actually what you do, you vaporize your molecule, and then you have here a cold finger or something, and then the crystals grow on there, because that is also a temperature gradient based thing. But you can easily imagine that your system has to be volatile. So it has to be able to go to the gas phase without destroying itself. And that's, we normally use the high vacuum for this. We have done this a couple of times, but it's a very, very complicated thing in general. Okay, we are closing down soon. The growing protein crystals is a special technique, and the idea is just show you briefly that we don't learn. So it's a hanging drop method. So you use this kind of a thing, and you have here protein crystals in a very low concentration inside the droplet, and here we have the reservoir. So that's the idea. It's also a concentration change happening in the droplet that causes this. Or you can have a standing droplet. So in principle, this is the same thing, but it's always inside. But nowadays, this was the classical way of doing this, but nowadays it's done on a plate, typically a 96 well plate, that each of them, in principle, in the best case, will grow one crystal only. But we don't use this technique. It is because this is for huge screening, so you have to do hundreds of thousands of experiments on that. And that's the idea how the protein crystallographers are doing. There are even instruments which can read this, is there a crystal or not. But in our case, we normally use our eyes and do it like this. Now, here are examples of crystals. This is a nasty case because there are two different crystals. We call it twin crystal. And in here you can see also, now you can see what happens when we use polarized light, that this is clearly not a nice part. It's crystalline, but it's bad. But there seems to be a nice place. So this is a single crystal, this is not. And you can see that crystals can have all kinds of shape and sizes and so on, but you never know if the crystal is good or not. So this good looks nice. If I see something like this, I guess, okay, yes, that looks like nice. And if you want to see nice crystals, if you have a table sugar, white table sugar or salt, these are very nice crystals. If you just put them in a black paper, you can see from your eyes, they're very nice cubes. And both are excellent crystals. So these are just examples of how polarized light can show us things. So if we have a good crystal, then it will shut down in the polarized light. When you use the polarized light in certain direction, it is killed. So it means that we have a continuous lattice in there. And again, some examples: good crystal, bad crystal, we can't be sure, certainly not the crystal, and so on. And this is actually the idea, that they can be, this could be a good crystal or not. I'm sure this is certainly nothing. This is a cracked crystal. It was okay, but it was taken out from the solution, then it cracks. We can't use this, of course. Very nice looking. Here might be, you can see it's a little bit soft on the sides. We can't be sure if it's okay. But there is no, we can't tell that in advance. How we attach the crystal then when it's done into the diffractometer, we need a sample holder, and this is a sample holder. And if you would be in my course in my university, we would go to the instrument, and then I will show you what it is. But this is roughly, this is what, in this case, I think 200 microns, so 0.2 millimeters. So it's really small. You have to, this is on the microscope. The instrument has a microscope. And that was last part of this. So this is what we are doing. We grow the crystals. We put it in this kind of a sample holder, and then we place it in the diffractometer. And then the measurement is completely different. We can't actually do this in this course. It's not needed, because what we now do with the next, we will jump from here to the phase. We have done the measurement on a good single crystal, how we can get the structure out of it. And this is what I will show you in the next lecture. And now we are 2 minutes over time, so we can have a short break of 5 minutes. Okay, let's do it like this. Now we are ready to go to do a real work. So now we have done the theory, we know what the X-rays are. We know that we need the instrument. This is the diffractometer, which is using X-rays, and we have to now record all the reflections coming from the crystal. And these crystals then appear as numbers from the instrument. And now we are really taking in their instrument data and start to look what is the structure, where does this diffraction come from. And now our target now is to use the data. We got it, somebody gave it to us, they made the measurements, and okay, here is the data. And they tell us, okay, it should be small chiral molecule. And this is now a walkthrough. I'm using a program set called OLEX2, and there is the link for this, and you can get it. It's free of charge. All the programs are available. You can use them. Its academy use is free. You don't have to worry about this. And there are other programs inside this OLEX2, but I'll show also. And we made it so that they will be available to you. We'll make a link. They're quite big, but you can do it easily and really easy install. So you can then install these programs to your own computer and do the work based on this, because you will also get the data. So you get exactly the same thing. So you can repeat the same thing what I'm doing here. You can do it at home with your own computer. And that's the essence in that sense. And then you can see actually what comes out. How does the real work, or how is the real work done with the programs? And that's the reason why I don't go into the mathematics on the theory part, because the computer programs are nowadays so sophisticated, we don't have to worry about. They know what to do. And it's our business just to follow and see that, okay, is this correct? Because one important point there is that the X-rays don't know the atoms. They only know the electron density. And this comes out from the programs. There are automatic programs there which analyze the data, and they guess. That will be the first guess. Okay, this could be the case. But now even that one appears in the new programs as an electron density, not a map, but appears like atomic balls. But they have you don't know. It's just a ball. And you will see later when I go through step by step what is the case. And this is really an exact thing how it's done in real life. So really, you can go there, and we will provide these things again. We will figure out the system, how you can get it, and then you can do it as you like. You don't have to, but if you are interested or you use X-ray diffraction on your own work and you are willing to do the work yourself, there might be a service measurements that they provide you the data. But if you are given the data with this, you should be able to do it yourself. Because it's not enough that you just do the structure, but you have to be able to analyze also the structure. And this we will do tomorrow. Tomorrow is the analysis part. And then finally, the last lecture is I will show you real examples over my career over the 30 years or so, different kind of supramolecular structures, what you can do with this. So this is, I would say, relatively simple work now. It's not very complex. And always in this course, I'm using excellent data. So there is nothing, no disorder or everything of this kind of a thing, that everything is as it should be. Of course, because you have to start from the good examples. So this is our target. And this is a typical way of getting information. So either you do it yourself, or then somebody have given you a sample. Normally there is at least a rough estimate about the chemical composition. So in here we have 13 carbons, 10 hydrogen atoms, 1 chlorine, 3 fluorines, 2 nitrogens, and 4 O atoms. So the molecular weight is about 330. It's a small molecule. And then tomorrow, or yes, in the lecture 10, I will show you structures where the molecular weight is 13,000. So it's a sizable small protein. But anything is done in the same way. It doesn't matter if it's a small molecule or a big molecule. the same thing applies. And then this is the cartoon of this. And now we already mentioned, okay, it's a chiral, but sometimes we don't know. We don't know, do we have an optically pure molecule, crystal, or do we have racemate? You remember racemate can crystallize also, and the pure enantiomers can crystallize. So in this case, we don't know yet if this is, we know that it's chiral, but we don't know if it's a pure enantiomer. And now it's a question, if it's a pure enantiomer, is it R or S or left-handed or right-handed? After that, we will know. So as I told you, X-ray diffraction is the only method which can reliably tell you what it is. Is it this one or that one? That's the beauty of this. So that's the idea. So we have a benzene ring here. Chlorine should be attached here. We have here a 5-membered ring with 4 different atoms. So carbons and O and nitrogen. And there is a nitro group here, a methyl group, and there's CH2 in here. And this is our target carbon. You can see from this carbon, sp3 carbon, there are 4 different substituents. So this is the chiral carbon. So we have here R or S. And now our idea is now to look into, we have the data, we got the data, and the data seems fine, so we start the business. We start the engine. So it looks like this. So the OLEX icon, when you install it, looks like this. So that's the idea. When it's there, we can click it, and we can start the engine. So the point, it opens, and the opening window, it looks like this. So we work this thing through these screenshots of the program. So there appears a text which happens in which time. So it's very easy for you to follow the handout, because you just follow exactly what is here in the handout with your own program, then you can easily get it. So the idea is that it looks like this. When you open it first time, there might be a structure coming up. And if you look very carefully, you can see this is sucrose. It's a sugar molecule. Because there is some demo structures inside the program, and it automatically, if you haven't done anything, opens one of them, and it's typically sucrose. So that's the idea. Don't worry about this. That might look different, as Oleg remembers the old work. And now it's sucrose. So that's the idea. And this is our graphics window, and there is some information in here. So now, what we do, we go in the upper left part here, and then say File Open. So we click this File Open, and so when we click the file opens, and click Open, a menu appears. So this is the walkthrough. So I've indicated each individual point what you have to click. Because of course you are not experts of using this program by itself, but now when you follow the walkthrough, then you can see what happens. Okay, it opens up a folder, and I normally always do it so that I indicate each structure has its own folder, because this program writes a lot of files. Some are needed, some are not, some are less important than the others, but they all go into one place. So that is very nice. So always give a name. Now here the name of this folder as a demonstration 25. And there are 2 files. And now these 2 files comes from the instrument. And now you can see there is an ins file. It's very easy to understand. It's instruction file. And this instruction file has a certain format, what the program on the diffractometer has already written. So it's ready to go. So it's our input file. It doesn't contain any information about the structure. It contains information about the unit cell and all the other things what the instrument can find out. But it doesn't know, of course, the structure. And then the HKL here is the data file. And now, remember, what is the HKL? HKL is the lattice plane, and HKL is the Miller index name for each plane. So this contains information on each of these planes. And there can be thousands of these. It's just a number. And now the idea in here is that we now go in here, select the demo and click Open. And now it doesn't open like this, but I show you how do they files look like. So this is now the demo ins. So the point is, this is directly written by the diffractometer program, but the idea is there. It tells that cell here, it's a parameter. This is our unit cell. So wavelength, A, B, C, alpha, beta, gamma. So you can see already, okay, it's orthorhombic system. Now, these are the errors. So this scans how many molecules we have there in the unit cell. It's 4. It's an orthorhombic system. It already, the diffractometer already guesses this. And then these are the errors. So this is the standard deviation of this. And now these don't have a standard deviation because it's fixed. It's an orthorhombic system. And now there's the information lattice. It says lattice type, lattice -1, primitive non-centrosymmetric. So the program already went through the data, and it says that, okay, now it seems to be the data speaks in favor that there is no mirror image in that. That is the non-centrosymmetric, so it's there. And now the symmetry operations, what are here, these are coming from the symmetry operations inside the unit cell. It thinks that it is. So it analyzes the data and sees, okay, it seems to be that these kind of asymmetries are there based on the diffraction. And then this scattering factor, these are information about atom types, which kind of atom types you have in the structure. This we have already given when we are doing this, because the program has to have an idea what are the atom types we have, because each of the atom type will diffract differently. The heavier atom, the more electrons there are, the stronger it diffracts. So we need to know them. We don't have to know them exactly, but if it's a big mistake here, it might cause some problems with the mathematics. And this is the actual how many atoms of these we have in the whole unit cell. So we in the unit cell have 52. Remember, it was C13. So 4 times C13 is 52. That's nothing more. So that is an information that comes from the instrument directly. And this is just an information about the format for this file. And now, this is now the HKL file. And this is how it looks. And look and see, 002, 002. 002 has been measured 2 times. And you can see the value is the same. And now, there is now, it's called the observed intensity. This is just a number. But this number now contains a tiny fraction of information of all atoms in the structure, but a very tiny one. So we have to collect all. Now you can see that it's the standard deviation. But now 003 is virtually 0. This is now 0. It means, okay, look, 003, where the L is odd, seems to be very small or 0. Look, 6, 0, 0, 3, minus. It seems that this 0, L equals an odd, is missing completely. And this is an information what you already, the program has seen. And based on that information, so it considers that the symmetry operations inside that unit cell are those. So the data contains information. This earlier we had to do this by hand. And we have to go through each of them and see ourselves. And you can see now that 4 is a big number, 6 is a big number, 8 is a big number, 10, 12, and so on. But you can see there's variations. What this means that now, if you look for this number, 0012, there is a lot of information coming. So the intensity is high. So it means that there has to be a lot of electrons on that plane. And in here, that's much less. There's virtually nothing, but still there. So that is the idea that these 2 files coming from the diffractometer are all we need. And there are, I can't remember, but we will soon see, I think some like a couple of thousand lines or whatever. So remember I showed you the CT scan of a brain, about 30 images. So you can consider each image is like this. So that is, it's measured twice, but anyway. So the idea in there is collecting, putting them all together will give us the structure. And now that's the idea, not the chiral carbon, that's the idea. So we have to figure it out. Is it enantiomerically pure or racemic? Now we start the engines. So now we click work here in the upper menu, and now it opens in this way. It doesn't know anything yet, but you can see the idea now. When we click open, it reads the ins file, and now you can see it wrote our supposed chemical information in here. And now reads the demo file and lists details in the upper side of the work menu here. That's the unit cell, that is the A, B, and C, that's the parameters and so on. These come from the old one, they doesn't relate to the structure at all. And then calculate Z. Z is the number of molecules in the unit cell and the total unit cell. And that's the idea. So we don't see anything else yet, okay? Now it reads in, now the data has been read in. Now we go in here, click the solve button. It opens, we activate this, the solve button here, and it gives us a new menu. So you can see this part changed now. And in here we have, so we have two phases. We have to solve the program. So there is the program what is guessing the phase. Remember the phase problem we had. So that if you don't know the phase, we can't solve the structure because it's needed. But the point in there is that there has to be some way to estimate the phase, and there's a program for this. And this is the solving program. The programs are here. There are several options. So what we have to do is to select a proper program here. Now the solve menu is now active. That's the yellow arrow here. And it shows the structure solution program and data file name and the chemical composition here. So now it says it reads the demo HKL file. It knows that it's there. All the data is there. And now the chemical composition is here. So in principle, we can change this if we like, but this is okay for us. Now, we think that is correct. Let's see what happens. So all these can be changed if needed. So we can have to do this. Okay, now, then we have to, because remember that the computer program in the diffractometer already was looking through the data and guessing or looking, okay, is the symmetry operations in this unit cell, can it find or some kind of thing, meaning that can it find the space group for this? The space group are the symmetry operations inside the unit cell, but we have to check this by ourselves. And there is a very nice button here, space group, suggest space group. So we click this, and it gives a listing of possible space group here down here. So when we click this, it will list here these things. And you can see here it says P212121, which was, by the way, the same what the diffractometer program was doing. It was doing a very superficial check, but this reads the whole data. So we have to believe this. And now in this phase here, that small number, you can see that there is a name for the space group. So now the program knows this, and it will use the symmetry operations, what was mentioned, for this space group with this unit cell. And if these both are correct, the mathematics should work. So now, let's see what happens. So we now go here in the program menu, and you will have it later on. We use a program called GIANxS. So that is a different set of programs. And by default, by teaching purposes, we are using an old version of a program which doesn't give everything at once. So it gives us a presentation of the electron density map. And this is the idea. So select this program menu here, and then click solve. So then when this is there, we will click solve here, and it runs the program. So it starts there. The computer is now running the structure solution program called GIANxS. There are many possibilities, I think 5 or 6 known of these kind of programs, but these select programs are very good, so we use this. So what happens then? Now, it did the program. It's nearly as fast as this. It happens in a second or so, and you get this kind of a strange looking blobs hanging in the space on this graphics window, and one is already green. So what happens? GIANxS program produces what we call the structure solution. This is not the structure. This is a structure solution. This is a guess. The program made a guess for the phases, and based on these phases, it puts up something. And now it's our idea to look, does it look reasonable? Was the guess for the phases mathematically close, so close that we can see a reasonable chemical structure? And now this reasonable chemical structure means electron density. And now the electron density already here is presented as balls, brown balls. So the idea is now visible. Some balls have color. The remaining brown ones are assigned electron density peaks. So we don't know what is the atom. We know that there's an atom. It seems to be that in this position, the brown balls, each of them represent an atom. But the point is there might be more of these peaks than there are real structures because we don't know what it is. So it's our business to start doing. So these are called Q peaks. We call them Q peaks. Q is unknown. And now the idea is that, okay, now we rotate the right mouse and drag. So you will show that in there. We rotate because it looks very bad. We can't see, it's just a blob. So we have to move it around. It's three-dimensional image. We can rotate and we will see something. So I will just show you before we go in there, how does it look? Because now in this phase, when we do this, this is based on another file, which is called the res file, the results file. So the structure solution writes as a results file into which it writes the coordinates of these things. And now when we look, it looks like this. That first part looks the same as in the ins file, but after that, you will see a list of coordinates. And now there is one which says chlorine, and there are the coordinates, and then Q1, and so on and so on. Why is this? Because now it sees that the peak height, the mountain, was much, much bigger than the others, and it knows that there's a chlorine. So the program automatically assigns that heaviest peak as a chlorine. All the others are unknown. So you can see it writes a new file, a results file, here a demo res, it contains electron density map with their here is the electron densities as a number. They are not related to any real numbers, but they are relative numbers. So that gives you, okay, you can see, if you look now carefully, start from 184, we go up there and it slowly goes down until 100 and then drops. So now if we start counting these things, it looks that there is exactly the same number of these heavier peaks that we have atoms in our structure. So it's promising. So that is the idea. Now, it has a maximum, is assigned, but now automatically write additional instructions here. We don't have to worry about this. Now we are back in here. Now I rotated that a bit. It looks different. It's the same blob. But now we look at on the different side, and now we can see that here we have a chlorine atom, which was already assigned, and then seems to be but now, if you look carefully, we know from the beginning that chlorine atom should be bonded to a benzene ring. So we should see a hexagonal blobs, hexagonal brown balls there. And that's the actual idea. Rotating a model known ChemDraw, that there should be a benzene ring into which the chlorine atom is attached. We can now edit the model. So we can here, we have possibilities now in here. You can see labels, carbon, hydrogen. We can use these and then start assigning the atoms or the brown balls to an atom. So what we click here carbon now, and lower left on the working menu activate the naming tool, and after clicking one by one, we start clicking 1, 2, 3, 4, 5, 6. And once we have done it, we have a benzene ring. And now you notice what happened. When I go backwards, look, there is no bond because it doesn't know what atom this is. But immediately when we assign that atom there as a carbon, it knows that, okay, the bond distance here is suitable for a carbon-chlorine bond, and it draws the bond. So now we have chlorine atom attached to a benzene ring. That's fine. Okay. Now what we do, the model looks like this. And now what we have to do, so we have a guess for the phases that they're good enough that we can see the benzene ring. But now the benzene ring, this is a guess. We have to make it more accurate. So what we now do, we take this part in here and we move it slightly and compare that with our data. This is called refinement. So we will have an accurate positions, more accurate, because now it's then, you can see, and then look carefully, they are all balls with the same size. The diameter of the ball has an importance. So we activate this menu here now, and now, okay, in here we must escape that we can get out from this thing, and we are now in there, and we go to the activation menu, refinement menu, and we click now, check a change refinement program is SelectL, because this changes. So each of these menu has different set of programs, and now in here, in this refine menu, which is now activated, we will select SelectL. That's a refinement program, and now we change now the cycles here, how many times it will change this. It's 4 times, and it will look for 20 additional peaks. So these we call the peaks. Can it find out a correct atom? So we do this. So now click the weight. There is a weight button here. This is a mathematical add-on. What we have to do is a correction factor, which always goes with it. So we click this, and then click the Ray Refine button here. Now something interesting happened. So look, there is again the blob of these brown balls, and now you can see that they changed the size of the balls. And now what is happening, it's estimating the thermal movement of the atoms, because all the atoms are vibrating. So it estimates their thermal movement of these atoms as a sphere. You can see there are different size. Don't worry about this. But now the idea is that now when we have done it first time, now we have a real comparison with our model, which is this, and the data. So we get so-called R value. So this is an information how well our model fits with the data. And this is what we are doing. So this is feels interesting in that sense when we have a data. Data contains all the information, and then we have more model. And now we have a partial model. So we don't see everything is here, but in this model we have only maybe 3 out of 5. So something is missing, and this is indicated by this number. So now around half of the structure is correct. So something is missing. As we know, there should be more atoms there when we have to locate all the atoms. So that's the idea. And notice the atoms of the model have changed now. And this we called an isotropic thermal motion. And the idea is that it's like a ball with its estimation the first time. It will be more accurate in the later. Okay, let's go on forward. And that's the idea of what we have in there. And now what we do, we change here now cycles to 10. So it will do more. So it will do more of these things, that it would stay, that we would have a really, there is no movement anymore. Because what we do in here, we just slightly move the atoms that it finds the correct position. It always compares that to the data. So now let's rotate this again and look if there are atoms attached to the benzene ring, and we name them as carbon atoms. And this is the idea. We found that there are 3 brown balls in there, and we just click them as carbon, and we have them now here. Now we go back to the refinement here and then see what we have. So now this number went down a bit, and we have now located that this looks fine, okay? And now if you look for the ChemDraw drawing, you know that there is a carbon, and into this carbon there are 3 fluorines atoms attached. So when we look carefully, we see that there are 3 brown balls in here, and I already activated them in here and asked the program now to change them to fluorine. So our chemical knowledge tells that there should be a CF group in here attached to, so here are the suitable peaks. I already activated them, and now I change them by this knob here, change them to fluorine. Okay, now we have that. We now go back again to this refine and then see what happens. Look, this number is going down all the time. So this number tells us that our model, what we are looking now, is now more accurate. It goes and fits better to the data. That's the idea. Now we can see, and also you can notice that the balls change slightly. They become more of a unique shape and size, but that's a movement. Okay, we have this here, and then the chlorines are there, additional brown beaks in there. Okay, now let's do a next step. Now the R value is this one. We also can use it as a fraction. And we can locate more of the missing atoms. So we rotate the model and see if we can locate more atoms. So we do this. And now what we can do in here, there is a nice knob in here that now, because the point is that the program doesn't know if the electron density is here or if the electron density is here. So it's just wants to have it, but it doesn't know if they are close by. So this collect knob is really nice because it will collect, it will look if some of these brown balls, the electron density peaks, are close to each other, and it moves them there automatically. So we click it there, and now it turns out to be that it seems to be really that there is a 5-membered ring in here. And now our chemical knowledge tells that we should have a CH2 group and a 5-membered ring attached. So look, seems to be that that could be the CH2 and that could be the 5-membered ring. Other peaks are also there, don't worry about it yet, but that's the idea. Well, let's see what happens. We start assigning them. Now select these peaks and we put them all as carbon atoms. In principle, they should not be carbon atoms on the 5-membered ring, but we just name them as carbon atoms. We know that all in here are not carbon atoms, but let's fix them later. And then do the refine, click here again, and now we see, okay, now look. Now it's 27 anymore. So it's going down. So our model, it gets more and more accurate. So now we see that there are 3 peaks close to the 5-membered ring. It would be the nitrogen O atom, the nitro group. So here, this thing. So now what we do, we rename them. So this would be nitrogen and O atom. And O atom, we rename it using this one, and then click this refine. Now we have a nitro group. And look, this dropped to 17. So the more atoms, correct atoms we find, the more accurate our model will be. That number will go down. So what we aim to do, to have this number as small as possible. And the OLEX is very nice in that it uses colors. So when you have a green, it's okay. Orange is somewhere there, but the red means this kind of, okay, be careful, not ready yet. And the point is now, the observed drastic drop in there because the only one atom is missing. So we have everything else except one atom is missing. We are now only looking for the amount of atoms. And the point, this is the CH3 group attached to the 5-membered ring, and you can see it here. So now we rename this as carbon and repeat the same refinement. Now we have it, and now observe, look. The R value went to 13 and changed color. So we are now going out from the red to the orange color or yellow. And now we have all non-hydrogen atoms. We can see that from our structure where the chemist gave us. Okay, yes, we have all the atoms. Seems to be that there is no other atoms. But now some of them are incorrect. So how do we know that they are incorrect? You can see the ball size here. The ball size here indicates thermal movement. And now the thermal movement is associated with the atom type, because each of the atoms have different amount of electrons, and then they diffract differently. So if we have an incorrect atom type, you can see this in the diameter of the ball. So clearly now, the idea is that the thermal movement of the carbon atom in the chiral center, okay, it's there. The item is now, sorry, you can't see it now, discuss about this, because we know that this carbon, which is hidden, I will show it in the program, there is an atom what we assigned as carbon, and that's really an O atom. So we have to change this. So we do this. So that one here at the back. So we go correct the atom type. This one here is not the carbon, it should be our O atom. we do this and now refine. The value changed a bit. Now atom type is correct, refine. The point, R value went down. So when we have a correct atom types in the correct positions, our model, so this is what we see here, fit better with the data. This is actually what we are doing. Now we have a correct atom type here, it's there. So observe our value is now, we have all the non-hydrogen atoms, some are still of incorrect type. So from the ChemDraw, we know that the 5-membered ring atoms opposite to the nitro should be O and nitrogen. And now they are carbons. And now if I have to make a guess, the actual idea is that because if we put here, instead of O atom, we put a carbon, it will have too much electrons for as a carbon, and it moves less. So this diameter of this ball is smaller. But we know that from the ChemDraw, so we don't have to guess. So at the point, we know that this has to be the O atom. So we rename it. We just click here and name it as a carbon, or sorry, O atom. And again, repeat the same thing. Now, the atom type is correct. And now we refine. We click here, refine. Again, the R value is going down. And now you can see that we have it there. Now the observed value is we have not all the atoms still one incorrect type. From the ChemDraw, we know that this is the idea, and rename now this as a nitrogen atom and repeat. And now it still goes down. Now all the atoms are now correct. And the point now, we can do a trick. We will go here and reduce the number to 5 and see what happens, and then refine it again. Now you can see when the refinement, you can see 5 Q peaks around the chlorine and fluorine atoms here. Look, why is this? The idea is that because we have now, until now, the program is using so-called isotropic thermal movement. It means that it's the same movement in all directions. But this is not real. So in the real life, the atoms are moving anisotropically, meaning that the thermal movement in this direction is different than this direction. So we have to change this here inside, because this is what we call the residual electron density here. This indicates that this atom is actually moving. And you can show that as the brown ball close to it. So what we have to do is we have to go here. There's a nice knob in here. Use anisotropic thermal parameters. So we click this. And now we refine as long as the weight, which is here now, it's green, but it will turn orange. But we will refine it as long as it's green. The green color is here. You can see a lot of green now already. So we do this. And now, with non-all, look what happens. 11.4, we change the atom types that they now are estimated. The thermal movement is taken into account, the real thermal movement. There's a drastic change. It drops to 4.8. And now it's green. And you can see how it appears. You can see ellipsoids in here now. And the idea is we go to the R value of 4.7, 4.8. And when the peaks are 5, we can see only 5 Q peaks, which should be hydrogen atoms. So our data is so good that we start seeing the ghost of a hydrogen. Hydrogen has only 1 electron, so it's not very good diffracting. But the idea we can see, okay, yes, there are. This could be the CH2 hydrogens. So let's do it. So we will change the peaks to 10. That's the number of the atoms, hydrogen atom in structure, and then refine. Again, go and refine and click. And now, look what we see. The R value didn't change, but we see 10 Q peaks, which look very suitable as hydrogen atoms. We don't know the hydrogen atoms because we don't have to, because there is a very nice knob here, add hydrogen. So the program can calculate the hydrogen in a correct position. So now we click this one, so calculate them by clicking add hydrogen button in the lower corner, and now we have. And the hydrogens appear as small white balls here. And now with all the others, our calculate R value is now 3.6. So we started from 50 and we go to 3.6. So this means an error of 100. So this is 100 minus this number correct. So the idea that it's now 96% correct. And it's really difficult to get lower because there is always some faults in the data. So this is our R value, which is a very good value. And now the remaining peaks here are the background. We don't have to worry about it. We have all the atoms. So we now do reduce the peaks to 10 and refine so that this goes like that. Now all is done. So this is our structure now. And you can see there is even hydrogen in the whole atom. They are all calculated in there. And now what we have to do, you can see that always been a red box here on this side. And this means that we have to ask the program to write one very important file. This is our coordination file called GIANxEFAML file. And then we change this to ACTA in here and refine everything to the completeness. And now you can see now ACTA is green, all these are green, these are all green, and then this is also green. So everything is done. We have now done the structure, everything is there. So the final structure has this structure solved and refined to completeness. This is now what we managed to do. This is the walkthrough of this thing. And now the question is, okay, what is this? But I will show you a thing. I will show that also in there because we have some time to do this. But now there is a more sophisticated program. And what happens, because this old program was giving you the electron density and you have to assign it yourself. But what happens with this? So you just simply go into this program here and then change the S to T and then click solve. Boom. This is what it gives in one shot. So the LXT solves the structure, assigns all the electron densities. When we have a good quality crystal like in here, you can assign nearly all atoms correctly. As the carbon and nitrogen atoms have only one electron difference, they're difficult. So now that we notice that in the 5-membered ring here, the nitrogen appears as carbon. Everything else, and now here, this nitrogen appears as carbon and this O appears as nitrogen. What we have to do is just to change this. And this is what we do. We now rename these correctly, make them anisotropic from there, and add hydrogens as we did it in the previous case and refine. And now we have the same thing. And this is the whole thing. I will demonstrate that with the CellXT now that it doesn't take too much time. So we are roughly on time. It takes about, I would say, 30 seconds, something like this. So all these things. So this is now the idea of refine everything. Everything's fine. You can see everything is green. And now you can see here a number. And this number appears only when we have a chiral structure with a pure enantiomer. And now we know that this molecule is enantiomerically pure and it's of correct handedness. And this is very important. There are values in here, and then this number is in green, then we know that we have a correct handedness. And it should be 0. If it's 1, then it's incorrect. And that's the idea. This is what the outcome is. So what we are doing here, actually, what we are making a model. And from this model, we calculate the intensities. So the intensities are actually changed, so-called structure factors. I didn't show the mathematics for this, but don't worry, the computer is doing that. So now our model we can use to calculate the numbers, the structure factors, and which are also from the data. And then this comparison is the R value. So the closer our calculated, the calculated is our model, and then the observed is measured, are similar, the smaller is the R value. And you can see they're very close. Look, tiny difference there, but in general, all these fit about 96%. And this is very good value. So then we are happy, everything is there, and that's the idea. This is just the standard deviation of these values. But that's what we do. We create from the electron density a map, electron density map, we create a model for our molecule and then compare these two things. And this is actually what we are doing. But now I will show you quickly the structure solution in real life. So here's the program. Their icon looks slightly different than what is in the Mac because they're in the Windows because this is the Mac version, but the program is the same. So it takes some time. It's rather slow to start. Hopefully it starts nicely. Let's see, it's there. It should be coming. Yes, it's there now. So we have it here. And now, this is now the thing. So you see how it is. What we do now, and don't worry about this. The Mac writes is different, but here we have here the open file. And now here we have it remembers because I was checking that. There we have the two files. So there's the data file and then the ins file, which is the same as you saw before. So what I will do, I will go in here and say open. And now it reads in the data. The data is there. And now you can see there is no information yet because we haven't done anything. So I will go now to the work. And now in the work here, I will click. I'm sorry, it went to incorrect. Sorry. I was too fast because my idea was to show you this now. So I was clicking the check the space group. So in there, it lists here now the space group, which is the symmetry operations. Okay, then it was too fast. I will do it again. Now you can see that the program is cellxt here. So I will ask it to solve the structure again. So it will say, are you sure that we want to solve this again? I won't, because I want to do it again for you. Now you can see what happens. So this is the speed. And now, this is now the thing, what you can do. What you're doing here, you're looking for your structure. You can see now there's a benzene ring here where the chlorine is already. Now it already assigns the fluorine atoms here. This is the chiral carbon. There is the O atom, CH2, and then the 5-membered ring. But you can see now there are mistakes. So this cannot be true. So this one has to be O atom. So I'll change that to O atom. Or this is not correct. This has to be nitrogen atom. So I do it like this. And now we know also that this one here is not carbon. So it's nitrogen. So I will assign that as a nitrogen. So now we have all the atoms. This is how it works. And now what we go here in this menu. I will activate it. Now is refine. And now you can see that I haven't clicked the weight yet, but I will just refine it. So it's 4 cycles. So let's see what happens. Now we got already 11% because it has all the atoms. We like a jumped to the station where we have all the atoms are there. And now you can see the balls are spherical because we have the isotropic thermal movement in there. So this is, you can see the weight is now red because I haven't clicked it. So I click it and redo this refinement. Now you can see that it gives, it's orange yet, but never mind, something is missing. So the weight has to be there because in the mathematical, it will balance between the calculated and observed values. So we always have to do this, but that's easy to do. It's just a follow. And you can see here a red tag here, which is how much our model is moving from the data, and we have to get this red one to green. So I will redo this. Now it went to green. So now we have all the atoms, but we have the isotropic thermal movement, which is the ball. So we have to change that to anisotropic, so that we will take into account. And that was this knob in here. So I will click this. It did it, and now we can see what happens. So the R value dropped to 7, and now the shape of the atoms changed to ellipsoid. And now you can see what happens. It's already assigned because I have here 11 peaks. So you can see now that, yes, There is one addition you can see here. This is clearly a ghost. It's not real because there can't be any hydrogen attached to this carbon or movement. But you can see here, this is nice. We can see a ghost. Obviously, they are hydrogen atoms. And I can even do it so that I can activate this atom now and then say add hydrogen. So it will now add hydrogens on the activated thing. And then I will say refine. And you can see this appeared. And this one here, which appears in this, is a ghost. So it's a background, it's nothing. Now, okay, I would be happy to have all the hydrogens placed in there. I click add hydrogens, and then I would refine. Now we're there, look. And as long as this goes green and this will green, we are happy, so we repeat it. Repeat it, we are there. Look now, all the numbers except this one is green. We have all the atoms, and these things here are background. You can see that there cannot be anything here between these two atoms, but it's a background. This is a typical thing of this, having these peaks. And these peaks, we can look the height of these peaks. I will look for example, this one. I will place this one here now. It gives a number, and it says this is Q4, and the height of this peak is 0.13, and hydrogen is 1. So we know that this cannot be anything because it's much less than 1. So we can in this way look. But this is normally how we do the work, but we have a model. So we try to solve them based on the model. Okay, we know that this is the structure, this should be the case. Like in this case, we have the 2chem drawing in here. So I will reduce these peaks. So we will leave only 1. And now this is the highest peak in the background. And you can see that it's between these two things. So we know that there is nothing. So we have all the atoms we have located. And now it's chiral molecules. So the point in there is that this number here indicates that we have the correct enantiomer and it's acceptable. But now the one thing is here that this is red. And then what we have to do is to change the octa and then refine it like this. And now it's interesting. So now I made a mistake in one step, that the amount of atoms which we located from the beginning, what we have, I will show it to you. In here, were not correct. So this can happen. So we find out some additional atoms, and then we know, okay, they are fine, but it's not taken into account, so it's very easy. You can see that it says that cell contents and the unit instructions list, meaning that that one doesn't agree. So we will now look carefully, because there are two things. I'm not sure if you know this. There are two possibilities now. Either my contents from the beginning was incorrect, or I have incorrect atoms in here. And now this requires a quiet. I'm not sure if even your boss realized this, that the computer program made a mistake. And this comes from the fact that the computer program doesn't know the atoms. The X-rays don't know the atoms, and they don't know how they are connected. So it's our business to see. And if you now remember, unfortunately, I don't have it, but if you remember the 5-membered ring, in the 5-membered ring, there is an sp2 carbon, which means that there's a double bond in there. In this carbon, this is also sp2. So if this hydrogen would be real, that would have a plus charge. And we would have to have an anion. So the computer was looking for it because it doesn't really know it. So it mathematically looks for the bond distances in here and there and says, okay, yes, it seems to be that there's a hydrogen missing from this atom, and it places that. But we were lucky enough that the computer program told us now there is something wrong. So we were sure that this is okay. But now the computer says, no, this is not the same as that one. And then realize, okay, chemically, this is impossible. So this, our understanding and knowledge about the chemistry what we have comes into a play. So we say to the computer program that you are incorrect. So we destroy this. We just go in there and, sorry, I will do it like this. This doesn't work so well. Delete. So I remove it. Now I repeat the refinement. And now once more. Now everything's green. Now we have done. And adding one hydrogen makes our structure completely incorrect. It cannot be correct chemically, but this number doesn't change virtually at all. So all the numbers were green, everything is fine, except there is the remark. So you have to be very careful when you have the structure, when you analyze the structure, that is chemically reasonable. Because the X-rays don't know. They don't know what atoms is and where is atom and so on. It only looks for the electron density. And we were not looking for the electron density in this area. It was just a computation what the computer was doing, the program. But that's that. So that's more or less, I think, everything what I want to show you today. Tomorrow, what we will do, we will go on, continue from this, analyzing the structure. What can we do with the structure? We can look for the bond distances and angles and packings and all these kind of things. And it's the analysis. And then finally, there will be a check if our structure is correct, is acceptable. And this is an additional thing we always have to do with the structures. And this process is called the GIANxEF. And that's why we have the ACTA here now. Where is it? ACTA here. That it writes, tomorrow I will show you the CIF file. And that's like the final file what we get from the structure solution. And there is additional service to check that everything is done correctly. And nowadays, when you are publishing a paper or you submit anything, you have to do the check. That everybody can see that you didn't cheat anything. So that's correctly done. But okay, that's that. So it took a little bit longer. But I hope that you get now an idea. So we will organize, discuss who wants to have these programs and so wants to play the game at home with your own computer so we can easily do this. And maybe tomorrow we will log that when we have a break time or so. What is the time for this? So, okay. Now everything is done for today. Tomorrow we continue. So thanks a lot. Thank you.
So, do we have time for a question answer session? Sure. So, yeah. Anyone? Oh, sure.
Sir,
Yes.
one method for crystallization, that is vapor diffusion method.
Yes.
So in vapor diffusion method, we have like select a small chamber inside a big chamber.
Yes.
And in a small chamber, we select a solvent where it is totally soluble
Yes.
molecule. And in bigger chamber, less soluble actually.
Yes.
Because it will create vapor pressure,
Yes.
but not interacting or less interacting with the molecule.
Yes. Yes.
Right?
That's the idea.
Yeah. So what if we choose insoluble in bigger size chamber?
You know, that should be, it should be so that it is insoluble for the bigger chamber,
Yeah.
because it will go from the bigger chamber to the small one where the solvent or the molecule is. So it's not the other way around. So it should be so, because if your compound would be soluble in the solvent in the bigger chamber, it would not crystallize. So that's the idea, because we have to change the concentrate or solubility of our target on in the small chamber, not in the big one.
Yes.
So that's the idea of what happens.
Okay.
So it's like mixing two things, and then the idea is that sometimes you do this you have solvent A and solvent B, and when you mix them, it changes color. So this is in principle the same thing. So we change the properties of that in the small one, and that will induce the crystallization. Okay?
Okay, thank you so much.
You're welcome.
Do remember that you guys have a test today, so please keep this session a bit short. You all will have time for asking professor the questions.
Yes, yes.
Good afternoon, sir.
Yep.
Sir, I have a question that do radioactive elements undergo diffraction?
So sorry, do what?
Do radioactive elements
Yes, of course. Yes, 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 yes. Any element will diffract. And the radioactive elements are normally the heavy, big ones, and they diffract extremely strong. So we have done work with uranium. It's not very radioactive, but they diffract in the same way as anything else. But of course, they are very dangerous to use because you can do this. I know it's been done, but then you have to have a protected environment because the crystal will also radiate. It will be radioactive. So it's exactly the same.
And so the last question is,
Yes.
you said up to minus 20 degrees Celsius, the
Yes.
crystal, the chemical properties like the orientation and the lattice energy
Yes.
of a crystal remains intact.
Yes.
So if the temperature goes down more, like if it comes to minus 25 degrees Celsius,
Yes.
so is there any deformation of the lattice orientation?
No, no. So the point is, I didn't tell you, but normally we measure everything in minus 150. So in the instrument, we cool down the crystal. But when it forms, then there's very seldom there is a big change. There can be so-called phase transition, but normally that's not the case. So when you get the crystal, then normally that will be stable in that on that temperature. So in that sense, it doesn't matter. It just forms in minus 20. And if you can keep it in minus 20 and put it in the diffractometer and then go even lower in the temperature, it doesn't change. But if you go higher, it will melt. So that's the idea. It's just when you get the crystal formation happening. That's only the point.
Thank you so much, sir.
Okay, thank you.
Okay, sorry to cut it short, but we are going to end the question answer
Yes.
session right now.
Yes.
So there are a few announcements for you all. So first of all, the lunch will be served at LHC Lecture Hall Complex. That's right opposite to this building. Okay, and LH4. Oh, sorry. Then it will be served at LH4 Dining Hall 2. That's like you have to walk across. Yeah, the canteen, main canteen. Okay, and the second announcement is with regards to your examination. The timing. It's from 2 p.m. and it's LHC, the building just opposite to this, room number 213. 2 means second floor. Okay, so you have to go to the second floor and find the 13th room there. Fine. And one more thing, if you are worried about the exam, please try to arrive 15 minutes earlier. You might get 15 minutes extra. So try to arrive at 1:45. Okay, that's all. Thank you.